Higher-order logic, HOL, is a powerful extension of classical first-order predicate logic. While first-order logic allows us to quantify only over individuals in a domain, higher-order logic permits quantification over properties, relations, functions, and even properties of properties. In this way, higher-order logic greatly increases expressive power and allows us to formalize many kinds of reasoning that are difficult or impossible to capture in first-order logic alone. The motivation for higher-order logic arises from both philosophical and mathematical considerations. In mathematics, many fundamental notions, such as sets of sets, functions on functions, and structural properties, are naturally higher order. In philosophy, higher-order logic allows us to speak about properties of properties and relations. In classical logic, we can easily formalize the sentence, "The house is red," but not the sentence, "Red is a color." In classical logic, it seems that red is a color must be treated as an atomic sentence. In higher-order logic, we can symbolize both sentences in a natural way. In higher-order logic, red is a color can be interpreted as saying that the property of being red has the property of being a color. Some philosophers and logicians believe that first-order logic is too restrictive and that higher-order logic more faithfully reflects ordinary mathematical and philosophical reasoning. In classical first-order predicate logic, property predicates and relational predicates are part of the language, but they cannot themselves be quantified over. We can say, for every individual X, but not for every property P or for every relation R. Higher-order logic removes this restriction. In second-order logic, we can quantify over properties and relations of individuals. In third-order logic, we can quantify over properties of properties and so on. More generally, higher-order logic allows us to speak about properties of properties of properties, potentially without bound. Thus, higher-order logic enables us to reason not only about individuals and their properties, but also about the properties and structure of those properties themselves. The syntax of higher-order logic extends the syntax of first-order logic. In addition to individual variables, we introduce predicate variables and function variables of various orders. Logical expressions are built using terms, constants, variables, logical connectives, quantifiers, and application of predicates to arguments. The grammar is typically governed by a type system that specifies which expressions can meaningfully be applied to which arguments. This prevents ill-formed expressions such as applying a term to a predicate or a predicate to itself in an unrestricted way. The semantics of higher-order logic is more complex than that of first-order logic. In general, models assign domains not only to individuals but also to properties, relations, and functions of various types. For example, second-order predicate variables may range over sets of individuals or relations between individuals. In full higher-order semantics, quantifiers range over all possible subsets, relations, or functions of the appropriate type. This makes higher-order logic extremely expressive, but it also leads to important metalogical consequences. One major philosophical issue in higher-order logic concerns paradoxes, most famously Russell's paradox. The paradox arises when we allow unrestricted comprehension over properties. Consider the set of all sets that are not members of themselves. Is this set a member of itself or not? If it is not, and if it is not, it is. But this is a contradiction. One influential response to this problem is type theory, which restricts how expressions can be formed by assigning them types. In type theory, objects, properties of objects, properties of properties, and so on belong to different levels, preventing self-application and thereby blocking paradoxes. Many modern formulations of higher-order logic are based on typed systems inspired by Russell's theory of types. There are several proof methods for higher-order logic. Some systems employ axiomatic calculi, extending those of first-order logic, while others use natural deduction or sequent calculi adapted to higher-order expressions. Lambda calculus plays a central role in many proof systems, especially in typed higher-order logics. Proof assistants and automated theorem provers often implement higher-order logics, using sophisticated algorithms to manage higher-order unification and inference. There are also Tableau systems for higher-order logic. Higher-order logic can be extended in various ways. It can be combined with modal logic to reason about higher-order necessities and possibilities, with temporal logic to reason about changing properties over time, or with epistemic logic to reason about higher-order knowledge and belief. Such combinations can be important in, for example, metaphysics, computer science, artificial intelligence, and formal epistemology, where rich, expressive frameworks often are required. From a metalogical perspective, higher-order logic differs significantly from first-order logic. Many classical metalogical results fail. In particular, full higher-order logic is not complete with respect to any recursively axiomatizable proof system, and it lacks compactness and the Löwenheim-Skolem property. These results are often seen as a cost of increased expressive power. However, some philosophers argue that this is a virtue rather than a defect, since higher-order logic more closely captures the intended meanings of mathematical concepts. Central logical notions can still be defined in higher-order logic. A sentence is logically true if and only if it is true under all interpretations of the appropriate kind. Logically false if and only if it is false under all interpretations, and logically contingent if and only if it is true under some interpretations and false under others. Logical consequence is defined in terms of truth preservation. A conclusion is a logical consequence of a set of premises if and only if every interpretation that makes the premises true also makes the conclusion true. An argument is valid if and only if its conclusion logically follows from its premises in this sense. In summary, higher-order logic is a rich and expressive logical framework that extends classical predicate logic by allowing quantification over properties, relations, and higher-order entities. While it sacrifices some of the elegant metalogical properties of first-order logic, it offers valuable tools for formalizing much of mathematics, philosophy, theoretical computer science, and similar fields. As such, higher-order logic occupies a central place in contemporary logical theory and its applications.